Picture this. You're standing alone on a hill at night. Above you, the sky is so clear, so deep, it feels like you could fall into it. Every star, every pinprick of light is part of a single, seamless tapestry. And the strangest thing, no matter where you look, the universe feels the same. Not just similar, identical, down to the tiniest whisper of temperature in the oldest light we can see. Now ask yourself, how is that even possible? Two patches of sky on opposite sides of the Earth, so far apart that light itself hasn't had time to travel between them since the beginning of everything, somehow agree with each other to better than 1 part in 100,000. It's as if two people on opposite sides of the planet, with no phones, no radios, no way to communicate, both wake up and say the exact same sentence at the exact same second in perfect harmony. That's not just odd. That's a cosmic riddle. And it's the first clue that our universe might not be all there is. Welcome to the moment modern cosmology began to suspect we're not alone. Not in the sense of alien civilizations, but in a much deeper, more unsettling way. The possibility that what we call the universe is just one room in a house so vast, we can't even see the walls. It all starts with a signal older than stars, older than atoms, older than time as we know it. This signal is the cosmic microwave background, the afterglow of the Big Bang. Discovered by accident in the 1960s, it's the oldest photograph we'll ever have, a baby picture of reality taken when the universe was just 380,000 years old. And when scientists mapped it in detail, first with satellites like COBE, then WMAP, and finally Planck, they saw something astonishing. The temperature of that light? Almost perfectly uniform, everywhere. To an astonishing degree of precision, it's 2.725 Kelvin, whether you look north, south, up, or down. The tiny ripples that do exist, they're smaller than a whisper, and they're the seeds of everything, galaxies, clusters, you, me. But the smoothness, the sheer sameness defied explanation under the old Big Bang model. Why? Because, in the standard view, the universe began as a hot, dense point and simply expanded. But if that's all that happened, regions now on opposite sides of the sky were never in contact. They couldn't have agreed on temperature. They were strangers, separated by distances too vast for even light to bridge in the time since creation. So how did they end up in perfect thermal sync? In the late 1970s, a young physicist named Alan Guth had a radical idea. What if, right at the very beginning, just a fraction of a second after time began, the universe didn't just expand, it exploded outward with unimaginable speed, not at the gentle pace of galaxies drifting apart, but in a runaway surge so violent, a region smaller than a proton ballooned to the size of a grapefruit in less time than it takes light to cross a single atom. He called it inflation, and it solved the puzzle instantly. Before inflation, everything we see, the entire observable cosmos, was packed into a tiny, connected region small enough to reach thermal equilibrium. Then, in a flash, it was stretched beyond recognition. The uniformity we see isn't a coincidence. It's a fossil imprint of that primordial intimacy. But here's where the story turns strange. Inflation, it turns out, doesn't stop everywhere at once. While it ends in our patch allowing matter, energy, and eventually stars to form, it may keep raging elsewhere. Like a pot of boiling water, where some bubbles form and stop growing, while the water around them keeps bubbling. Each bubble where inflation ends becomes a universe of its own. And between them, an eternally inflating sea, spawning new bubbles forever. This isn't science fiction. It's a direct mathematical consequence of the simplest models of inflation. Models that also explain the features we do observe in our cosmic background. In fact, the pattern of those tiny ripples, their size, distribution, and polarization, matches inflationary predictions with eerie accuracy. So, if inflation is real, and if it's eternal, then our universe is just one bubble in a vast, possibly infinite, multiverse. Each bubble universe could have different laws of physics, different constants, different numbers governing how forces behave. Some might collapse instantly. Others might never form atoms. A rare few, like ours, might be just right for stars and life. Now, let's be clear, we have no direct evidence of these other bubbles. We can't see them. We can't visit them. They lie beyond our cosmic horizon, a boundary not of distance, but of time and causality. Light from those regions will never reach us because the space between us is stretching faster than light can cross it. But that doesn't mean the idea is unscientific. It means we're at the edge of what observation can reach. And sometimes, science advances not by seeing, but by inferring. By following the logic of our best theories to their natural conclusions, even when those conclusions unsettle us. Think back to that night on the hill. You looked up and saw unity, a sky that felt whole. But that very unity, that perfect smoothness, might be the first echo of a much grander reality, a multiverse born from a single, fleeting moment of cosmic inflation. We didn't set out to find other universes. We set out to understand why our own is so strangely harmonious. And in answering that, we may have stumbled upon a truth far larger than we ever imagined. The mirror in the sky didn't show us a reflection of ourselves. It showed us a fragment of something vastly bigger, and it whispered, "You are not the whole story." Imagine you're walking through a garden at dawn. Dew clings to every leaf. The air is still. And every path ahead of you forks, not just once, but endlessly. Turn left, and maybe you meet someone who changes your life. Turn right, and you never do. Stay still, and time still moves. But what if every choice you could make is made just in another version of this garden? This isn't a metaphor for regret or possibility. This is the startling claim of one interpretation of quantum mechanics, the many worlds interpretation. And it suggests that the multiverse isn't just out there, beyond the edge of space. It's being born inside every atom, every instant, right here. To understand how, we have to go back to the early 20th century, when physicists discovered that the tiniest pieces of reality don't behave like tiny billiard balls. Electrons, photons, even entire molecules, they exist in states of potential. An electron doesn't have a fixed position until you measure it. Until then, it's described by a wave, a mathematical cloud of probabilities spread out over space, humming with all the places it might be. This isn't because we're ignorant. It's because nature itself is fuzzy at the smallest scales. The universe, it seems, doesn't decide what's real until it's forced to. And that's where things get weird. In the 1930s, the standard view, called the Copenhagen interpretation, said that when you observe a quantum system, this wave of possibilities collapses into one definite outcome. You open the box, and Schrödinger's cat is either alive or dead. Before that, it's in a ghostly limbo of both. But this raised a troubling question. What counts as an observation? Does it need a human, a camera, a single atom bumping into another? The theory never said. It just drew a line between the quantum and the classical. And that line felt arbitrary, like a stagehand stepping into a play and saying, "Now it's real." Then, in 1957, a quiet Princeton graduate student named Hugh Everett proposed a daring alternative. What if the wave never collapses? What if all the possibilities are real, and every time a quantum event has more than one outcome, the universe splits? Not metaphorically, not philosophically, literally. In Everett's view, when you look in the box, there's no collapse. Instead, you become entangled with the system. One version of you sees a living cat. Another version, just as real, just as conscious, sees a dead one. Both outcomes happen, but they happen in separate, non-communicating branches of reality. The universe doesn't choose, it multiplies. This is the quantum garden. Not a place of what-ifs, but of what-is. Every quantum interaction, from a photon hitting your eye to the decay of a radioactive atom in a rock deep underground, sends out new shoots, new branches. And because quantum events happen constantly, everywhere, the number of branches grows at a rate beyond comprehension. Not millions, not billions, a number so vast it makes the stars in our galaxy look like dust motes. And you're in all of them. Or rather, versions of you are. In some, you're reading this sentence. In others, you paused to look out the window. In others still, you never clicked play on this video. Each decision you feel you make is just you becoming aware of which branch you're on. But every other choice lives on in another world. Now, this sounds like fantasy. But here's the twist. The many worlds interpretation isn't some fringe idea. It's one of the leading interpretations of quantum mechanics among working physicists, especially in fields like quantum computing and cosmology. Why? Because it removes the arbitrary collapse rule. It treats the entire universe as a single quantum system, evolving smoothly according to the Schrödinger equation, the core law of quantum theory, without exceptions. There's no magic moment when reality decides. There's just wave functions evolving, interacting, branching. The math works, it's clean, elegant, and it fits everything we've observed in the lab. Every double-slit experiment, every quantum interference pattern. It's all consistent with a reality that never collapses, only divides. But if that's true, where are these other worlds? Why can't we see them? Because once branches split, they decohere. That's a technical word for a simple idea. They stop interfering with each other. Imagine dropping two pebbles in a pond. At first, their ripples cross and mingle, but as they spread, they become independent. You can't tell they ever interacted. That's decoherence. Once two quantum branches separate, they evolve on their own, like parallel rivers that never meet again. No signal, no light, no influence can cross between them. They're causally isolated, not by distance, but by the very structure of quantum information. So these other worlds aren't far away in space. They're right here, but orthogonal to our experience, like pages in a book that never touch, even though they're bound together. You share a past with your other selves, but not a present, and never a future. Critics say this is untestable, and they're partly right. We can't access those branches. But that doesn't mean the theory is meaningless. Just as we accept electrons exist, even though we can't see them directly, we can accept branching if it's the simplest explanation that fits the data. And for many it is. Yet there's a deeper unease. If every possibility happens, does anything matter? If there's a world where you succeed and another where you fail, is choice an illusion? But pause. Think carefully. In your branch, your choices still have consequences. The version of you reading this feels hope, doubt, curiosity, just as real as ever. The existence of other branches doesn't erase your pain or your joy. It just says reality is bigger than your single story. And strangely, this view restores a kind of cosmic democracy. In the Copenhagen picture, only one outcome is real, chosen by a mysterious act of observation. In many worlds, all outcomes are honored. No possibility is discarded. The universe doesn't gamble. It embraces every roll of the dice. But here's the quiet irony. This quantum multiverse has nothing to do with the cosmological multiverse from inflation. One comes from the physics of the very small, the other from the physics of the very large. They arise from different equations, different domains. Yet both point to the same humbling truth: our universe may be just one thread in a much richer tapestry. So the next time you face a choice, big or small, remember the garden. Not as a place of escape, but as a reminder, reality is more generous than we imagine. It doesn't force us down one path. It lets every path bloom, even if we only walk one. There's a story physicists sometimes tell about a traveler who climbs a mountain to meet a sage. "What is the universe made of?" he asks. The sage smiles and hands him a map, not of the world, but of every possible world. This, he says, is the real terrain. That map is not fantasy. It's called the string theory landscape. And it may be the most controversial and most profound attempt yet to explain why our universe has the rules it does, and whether those rules are unique or just one option among a near-infinite menu. To understand how we got here, we have to go back to the dream that launched string theory, the dream of a single equation that unifies all of nature. For centuries, physics progressed by finding deeper connections. Electricity and magnetism became one force. Space and time merged into space-time. Matter and energy revealed themselves as interchangeable. By the late 20th century, scientists hoped to go further, to describe gravity and quantum forces under one roof. That's where string theory entered. Instead of treating particles as points, string theory says the fundamental ingredients of reality are tiny vibrating loops. Strings so small that if an atom were the size of the observable universe, a string would be no bigger than a tree. The magic is this: the way a string vibrates determines what kind of particle it is. One note makes an electron, another a photon, a deeper, slower hum gravity itself in the form of the graviton. For a while, it seemed like the final theory was in sight. But then, something strange happened. As researchers dug deeper, they discovered not one version of string theory, but 5. And worse, each required more than the 3 dimensions of space and 1 of time that we experience. They needed 10 or 11 in a later extension called M theory. Where are these extra dimensions? The idea is that they're curled up, compactified into shapes so tiny they're invisible to us, like a garden hose that looks like a line from far away but is really a cylinder up close. But here's the catch: there are countless ways to curl them up. Hundreds of thousands, millions. Some estimates suggest as many as 10 to the power of 500 distinct configurations, each one a different geometry, each one giving rise to different laws of physics in the 4 dimensions we see. This is the landscape. Not a physical place, but a vast mathematical space of possibilities. Each point on it represents a possible universe, with its own particles, forces, constants, even numbers of dimensions that appear large. Some have strong nuclear forces that bind atoms tightly. Others have gravity so weak that no stars ever form. In some, electrons are heavier than protons. In others, electromagnetism doesn't exist at all. And our universe, it's just one point on this landscape, a tiny oasis where the numbers allow atoms, chemistry, planets, and us. The strength of gravity, the mass of the electron, the energy of the vacuum, these aren't dictated by a single beautiful equation. They're environmental, accidental, like the climate of a single valley in an endless mountain range. This was a shock. For decades, physicists believed the laws of nature were unique, inevitable, like the digits of pi. But the landscape suggests otherwise. The laws we see may not be fundamental at all. They may simply be the local bylaws of our cosmic neighborhood. How did we end up here, in this particular valley? That's where cosmology and string theory meet. Remember eternal inflation from Act 1? It doesn't just create bubble universes, it can populate the landscape. As inflation ends in different regions, the extra dimensions settle into different shapes, like water freezing into different crystal forms depending on temperature and pressure. Each bubble becomes a universe with its own physics, drawn randomly from the landscape's menu. So the multiverse isn't just many universes, it's a mechanism for sampling every possible universe that string theory allows. And if there are 10 to the 500 options, and inflation creates infinitely many bubbles, then every possible universe that can exist does exist somewhere. This idea found powerful support from an unexpected source, the mystery of dark energy. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating, not slowing down as expected. Something invisible, dubbed dark energy, is pushing space apart, and its strength is astonishingly small. Not 0, but 120 orders of magnitude smaller than naive quantum theory predicts. So tiny, in fact, that if it were just a little stronger, galaxies would never have formed. A little weaker, and the universe would have collapsed long ago. Why is it so finely tuned? In a single universe view, this seems like a miracle. But in the landscape multiverse, it's inevitable. Among countless bubbles, some will have dark energy values that allow structure and life. We live in one of those. Not because it's special, but because only in such places can observers arise to ask the question. Critics call this reasoning circular. You're just saying we see this value because we're here to see it, they argue. And that's true. It's called the anthropic principle. But when used carefully, it's not a cop-out. It's a selection effect, like realizing that fish only exist in oceans, not because water is designed for fish, but because fish can't exist without water. Still, many physicists recoil at the landscape. They worry it marks the end of predictive science. If every constant is random, how can we ever explain why things are the way they are? Nobel laureate David Gross called it giving up. Others, like Leonard Susskind, argue it's the only honest response to the math we have. And the math is stubborn. Despite decades of effort, no one has found a principle that picks out our universe as unique within string theory. The landscape remains, not proven, but persistent. Like a shadow at the edge of understanding. Worse, we may never directly test it. The extra dimensions are too small to probe, even with the largest particle colliders. The other bubbles are beyond our horizon. So is the landscape science, or speculation dressed in equations. Here's the subtle truth. Science often advances through indirect inference. We never saw atoms directly until recently, but their effects were undeniable. We've never visited a black hole's event horizon, but we trust general relativity because it works everywhere else. The landscape may be the same, a prediction of our best attempt to unify physics even if we can't visit every corner of it. But it demands humility. For centuries, we assumed the laws of nature were written in stone. Now we wonder, are they more like regional dialects shaped by history, chance, and cosmic geography? And if so, what does that say about the dream of a final theory? Maybe the universe isn't governed by a single equation. Maybe it's governed by a library, a vast, silent library where every possible story of physics is written, and ours is just one page, lit by the brief flame of our curiosity. We set out to find the ultimate laws. Instead, we may have found the ultimate plurality. Not one universe, not one set of rules, but a cosmos of endless variation, where the only constant is possibility itself. Imagine you're standing on the shore of an ocean at night. The water stretches before you, black and endless. You know the ocean continues, miles, hundreds of miles, maybe forever. But no matter how powerful your flashlight, no matter how high you climb, you can never see beyond the horizon. The curve of the Earth hides everything past a certain point. Now imagine that horizon isn't made of water and sky, but of time, space, and causality itself. And beyond it, other universes, other laws, other versions of reality, entire cosmic histories playing out in silence, forever inaccessible to us. This is the dilemma of the multiverse. It may be a natural consequence of our best scientific theories, and yet lie permanently beyond observation. So the question isn't just, is it real? But can it ever be science? Science, at its core, is built on testability. A theory must make predictions that can, in principle, be confirmed or falsified by experiment or observation. That's what separates physics from philosophy, and philosophy from poetry. But if other universes are causally disconnected from ours, if no signal, no particle, no influence can ever cross the gap, then how can we test their existence? Some critics say we can't, and that the multiverse, therefore, isn't science at all. Philosopher Karl Popper argued that for an idea to be scientific, it must be falsifiable. If nothing could possibly prove it wrong, then it's not a scientific claim. By that standard, the multiverse fails. But others push back. They say science has always dealt with things we can't directly see. We accept the existence of the interior of black holes, even though nothing escapes them. We believe in the first fraction of a second after the Big Bang, even though we can't observe it directly, only its echoes. In each case, we infer hidden realities from their footprints in the observable world. So could the multiverse leave footprints? Possibly. One idea, wild but mathematically coherent, is that if our bubble universe once collided with another during the early stages of inflation, it might have left a bruise in the cosmic microwave background, a cold spot, a ring of unusual polarization, a scar in the oldest light. In 2014, a team of researchers claimed to have found just such a pattern. A circular anomaly in Planck satellite data that matched simulations of bubble collisions. But follow-up studies were inconclusive. The signal could also be explained by ordinary cosmic variance, a statistical fluke in the noise, no smoking gun. Other proposals are more indirect. If the multiverse explains why our constants are fine-tuned like the value of dark energy, then its explanatory power becomes a kind of evidence, not proof but plausibility. After all, if you find a watch in the desert, you don't need to see the watchmaker to infer design, or, in this case, selection from a vast ensemble. Yet, that's where many scientists draw the line. Explanatory elegance isn't the same as empirical evidence, and leaning too heavily on the anthropic principle, saying we see this because we must, risks turning science into storytelling. There's another layer to this tension. Modern physics has reached a frontier where experiments are becoming impossibly hard. To probe the energy scales where quantum gravity operates, we'd need a particle accelerator the size of the solar system. To observe the extra dimensions of string theory, we'd need microscopes that resolve distances a billion times smaller than an atom. In this new era, theory may outpace experiment for generations. And when that happens, how do we decide which ideas are worth pursuing? Do we follow mathematical beauty, consistency, predictive fertility, or do we wait, perhaps forever, for data that may never come? This isn't just about the multiverse. It's about the soul of science. Consider the history of atoms. In ancient Greece, Democritus proposed that everything was made of indivisible particles. For 2,000 years, it was pure philosophy, untestable, unverified. Only in the early 20th century did Einstein's work on Brownian motion, and later experiments by Rutherford and others, turn atoms through speculation into fact. So maybe the multiverse is like atoms in the year 1800, real but not yet reachable. Or maybe it's like the ether, a compelling idea that ultimately leads nowhere. The difference is humility. Real science admits uncertainty. It says, here's what our equations suggest, here's what we can test, here's where we're guessing. The danger isn't in speculating, it's in forgetting that we're speculating. And that's why the multiverse debate matters. It forces us to ask, what counts as knowledge? When does a mathematical consequence become a physical reality? And how much of the cosmos are we willing to accept as real, even if we can never touch it? Some physicists argue that if a theory is our best explanation for everything we can see, and it implies other universes, then we should take those implications seriously. That's how we accepted the existence of quarks, even though they're permanently confined inside protons. We never see them alone, but the model works too well to ignore. But others warn of a slippery slope. If we start accepting unobservable entities because they make our equations tidy, where do we stop? Could we end up with infinite layers of untestable structure, elegant, self-consistent, and utterly disconnected from reality? There's no easy answer. But perhaps the most honest response is this: the multiverse may be science in progress. Not settled, not proven, but a live possibility emerging from our deepest theories. And in science, possibilities deserve space to breathe, as long as we remember they're not yet truths. We stand at the edge of knowing, not because we're ignorant, but because the universe has horizons built into its very fabric. And sometimes the most profound discoveries aren't new objects, but new limits to what we can ever know. So we keep looking. Not just outward, but inward, questioning our methods, our assumptions, our definitions of evidence. Because the quest isn't just to map reality, but to understand what it means to know anything at all. And in that questioning, we remain scientists. Not because we have all the answers, but because we refuse to stop asking. Look around you, not just at the screen, the room, the sky, but at the invisible scaffolding beneath everything, the strength of gravity that lets stars burn for billions of years, the precise mass of the electron that allows atoms to bond into molecules, the delicate balance between nuclear forces that lets carbon, the backbone of life form inside dying stars. Change any of these numbers just a little and the universe becomes sterile. No stars, no chemistry, no planets, no us. This is the puzzle of fine-tuning. And it's not a philosophical whim, it's a measurable fact. The constants of nature appear to be balanced on a knife's edge. Tilt them slightly in any direction, and the cosmos falls into silence. Why? For centuries, this question lived in the realm of theology or metaphysics. Some saw divine design, others saw cosmic luck. But in modern physics, it has become urgent, because our best theories not only confirm the fine-tuning, they deepen it. Take the vacuum energy, the energy of empty space, responsible for the accelerating expansion of the universe. Quantum field theory predicts it should be enormous, driven by fluctuations of virtual particles popping in and out of existence. But when we measure it, it's almost zero. Not just small, astonishingly, unnaturally small. So small that if it were just a few times larger, galaxies would never have formed. The universe would have ripped itself apart before the first star could ignite. The discrepancy between prediction and observation, 120 orders of magnitude. That's not a rounding error, it's the worst mismatch in the history of science. Or consider the initial conditions of the Big Bang. The universe began with near-perfect uniformity, but with just enough tiny ripples to seed galaxies. Too smooth and nothing ever clumps. Too lumpy and black holes dominate everything. The odds of such a Goldilocks start are astronomically low. And then there's the ratio of matter to antimatter. In the early universe, for every billion antimatter particles, there were 1,000,000,001 matter particles. When they annihilated, that 1 in a billion surplus became everything we see. If that asymmetry was zero, total annihilation, a universe of pure light, no atoms, no structure, no observers. So again, why this universe? Why these numbers? One answer, bold and controversial, is the multiverse. If there are countless universes, each with different laws and constants, then it's no surprise that at least one of them is hospitable to life. We don't need a tuner. We just need a vast enough ensemble and a selection effect. We're here because only here can here exist. This isn't magic. It's probability. Imagine rolling a die with 1,000,000 sides. The odds of rolling a 6 are tiny. But if you roll it 1,000,000,000 times, you'll get plenty of 6s. Our universe is that 6. Not special in itself, but inevitable in a vast enough sample. But here's the unease many feel. Does this explanation explain anything? Or does it simply push the mystery one level up? Now we must ask, why does the multiverse exist? Why does it produce such variety? Why do its rules allow life-friendly pockets at all? And worse, does it rob the universe of meaning? If every possibility exists, then our existence feels less like a miracle and more like a statistical inevitability. Like finding a single grain of sand on an endless beach and saying, this one is special. Yet consider this, the multiverse doesn't make our universe less rare. It makes our experience of it more precious. Because in all the countless branches, all the sterile voids, all the collapsing bubbles, only in universes like ours can questions like this even be asked. Consciousness, curiosity, awe, these are not guaranteed. They are fragile flowers that bloom only in very specific cosmic soil. And that brings us to a deeper point. The fine-tuning problem may not be about numbers at all, but about the nature of physical law itself. Why do we have these laws and not others? Why is the universe comprehensible? Why do mathematical equations describe reality so precisely? Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." That's not a scientific statement, it's a wonder-filled observation. And it hints that the mystery runs deeper than constants and parameters. Perhaps the multiverse is a placeholder, a bridge between what we know and what we don't. It offers a naturalistic answer to fine-tuning without invoking a designer. But it also highlights how little we understand about why any universe exists, why there is something rather than nothing. Some argue that even if the multiverse exists, it doesn't eliminate the need for explanation. Because for the multiverse to generate life-permitting universes, its own meta-laws must be finely tuned. The rules of inflation, the structure of the string landscape, the mechanism of quantum branching. These too must allow for variation within life-permitting bounds. So, the fine-tuning may just be relocated, not resolved. Others counter that maybe, in a truly fundamental theory, all possibilities are allowed, and our universe is simply one that can ask questions. In that view, the act of observation isn't passive. It's part of the universe becoming aware of itself. This isn't mysticism. It's a recognition that science and meaning are not enemies. We can accept natural explanations and feel awe. We can understand the physics of starlight and still be moved by its beauty. The multiverse, if real, doesn't diminish our place. It reframes it. We are not the center of all reality, but we are rare witnesses to it. And that rarity matters. Because in a silent, indifferent multiverse, the fact that this universe contains beings who can ponder their own existence, that is extraordinary. Not because it was destined, but because it was improbable. And in that improbability lies a kind of grace. So when we ask, why this universe? We're not just asking about numbers. We're asking why there is a stage where questions can be asked at all. The multiverse may be the answer physics gives, but the wonder? That belongs to us. We began this journey at the edge of space and time, chasing echoes of the Big Bang, tracing quantum branches, mapping hidden dimensions. We followed the math wherever it led, even when it pointed beyond the horizon of observation. But now, at the end, we return not to equations, but to something quieter, closer, ourselves. Because the multiverse isn't just a scientific idea, it's a mirror. And in its infinite reflections, we see our oldest hopes, our deepest fears, and our unshakable need to matter. Long before physicists spoke of bubble universes or quantum branches, humans told stories of other worlds. The Greeks imagined the Isles of the Blessed, where heroes lived in eternal spring. Indigenous cosmologies speak of layered realities, spirit worlds intertwined with our own. In Hindu thought, universes are born, live, and die in cycles as natural as breath. The multiverse, in one form or another, has always lived in the human imagination. Why? Because we feel the weight of choice, the ache of paths not taken, the haunting thought, what if I'd said yes? What if I'd stayed? What if I'd been born elsewhere, else when? The multiverse gives those ghosts a home, not as regrets, but as realities. In some branch, you took that job. In another, you reconciled with someone you lost. In a universe shaped by different chance, you're still whole. That's powerful, healing even. But it's also dangerous. Because if every version of you exists, then nothing you do truly matters, since another you undoes it or suffers for it or never cared at all. Meaning becomes diluted across infinity. Responsibility evaporates. Why strive if every failure is balanced by a success somewhere else? But here's what the science quietly corrects, even if other versions exist. This version, you, reading this, feeling this breath, carrying this history, is real. Your pain is real. Your joy is real. The love you've given, the mistakes you've made, they belong to this branch, this timeline, this irreplaceable thread of experience. The multiverse doesn't erase your story. It just says your story isn't the only one. And that's liberating, not diminishing, because it frees us from the tyranny of the one right path. Life isn't a single line from birth to death. It's a cascade of moments, each opening new possibilities. The multiverse, in its scientific and poetic forms, reminds us you are not defined by your worst choice or your best. You are part of a vast, unfolding becoming. Yet there's another human hunger the multiverse speaks to, the desire to believe the universe is for us, that our existence means something in the grand scheme. For centuries, we placed Earth at the center of creation. Then we learned we orbit an average star in an ordinary galaxy, in a cosmos billions of light years across. We felt small, adrift. The multiverse makes us feel even smaller. Not just one planet among billions, but one universe among possibly infinite. In that scale, it's easy to conclude we don't matter. But that's a category error. Importance isn't about size. A single note isn't important in an orchestra because it's loud, but because it's necessary. Without it, the harmony breaks. In the same way, consciousness may be rare, but it's not irrelevant. We are the universe reflecting on itself. The only known place so far where Stardust has learned to ask, why? And that act of questioning changes everything. A silent multiverse is just physics, but a multiverse that contains beings who wonder about it? That's something new, something unprecedented. Maybe even something sacred, not in a religious sense, but in the sense of awe, of reverence, for the sheer improbability of awareness. So the human multiverse isn't about parallel selves. It's about the stories we tell to make sense of being here, now, in this particular unfolding of reality. Science gives us one story, a cosmos born from quantum fluctuations, shaped by inflation, fine-tuned by chance. Religion offers another, creation with purpose. Philosophy, still another, meaning we make for ourselves. These aren't enemies. They're different languages for the same wonder. The multiverse, in the end, doesn't answer the human question. It reframes it. Not are we alone, but what do we do with the fact that we're here at all? And the answer isn't in the math, it's in how we live, in how we treat each other in this world, on this earth, in this fleeting moment of cosmic clarity. Because whether or not other universes exist, this one is ours to care for. This pain, this joy, this fragile web of life, it's real to us, and that's enough. So let the multiverse be a reminder, not that we're insignificant, but that significance is something we create, not by being the center of everything, but by being present in our own story, by choosing kindness when we could choose indifference, by seeking truth when we could settle for comfort, by looking up at the stars and feeling not small, but connected to the past, to each other, to the great mystery that birthed us. In the end, the multiverse isn't out there. It's in here, in our capacity to imagine, to question, to hope. And that, more than any bubble or branch, is the true frontier. Because the most astonishing thing in any universe is a mind that can wonder about it.